All right, I think I'm live now. We'll get started in just a few minutes once I see that there's more viewers on the stream. Testing the audio. Can someone type in the chat if you can hear me and see me? Excellent. All right. Thank you all. I'll wait just another minute or two, because right now there's still just 9 people here. Hope project 2 is going well for all of you. Good point, Colton. Yeah. Due date's coming up pretty quickly. All right, we've got a reasonable number of people on the stream now, so I'm going to go ahead and get started. Before we jump into the lecture, there's 3 things to mention. First of is introductions. Most of you probably have not seen me since lecture 1, unless that is you come to my office hours, in which case maybe you've seen me more recently. But my name is Max Krogius. I am a 4th year PhD student in the robotics program. And so most of my work is on robots, of course, little ground robots that drive around and try to, so my work is on how they plan around other agents in the environment. So basically, how do you make assumptions about what things other people are trying to do, and how do you accomplish your own goals while other people are trying to accomplish their goals. So I've been here for 4 years now, but before that I was a software engineer at Google for a couple of years. And before that I did my undergrad in physics at McGill University in Montreal, Canada. So that's the first note, introductions. Second note is the audio quality. So unfortunately, I had 2 microphones and 1 webcam die on me yesterday. I managed to borrow a replacement, but I realized the audio quality isn't quite as good as it could be, and by the next lecture, I will have replacement. So that should get sorted out. I think there's a lesson here for any computer science student or practitioner, which is that technology always fails, and often at the worst possible time. So in this case, right before the live stream of this lecture. So anytime you've got a demonstration coming up, always double check everything's working, even if you've already tested it who knows how many times before. I'm seeing a note in the chat about why is the screen blurred. Hopefully that's just this slide. Can someone say if this slide is fine? I think the image on this slide is just a little bit blurry for the midterm schedule. Okay, cool. I'm going to go ahead. There's not too much I can do about it anyways, but I'll check the video after the lecture and make sure that everything's fine. Okay, so some mixed answers in the chat. Well, okay, so in what way is it unstable? Is it buffering or is it just low resolution? Yeah, hopefully it's just one person's individual connection. Here it says that my connection is pretty good, so I think we'll move ahead. And if it's a problem, hopefully I'll have it fixed for next time. Right, so third note is about lecture and midterm schedule. So today, let's see if I can get a laser pointer. Yeah, there we go. Today is Tuesday, October 13th, where you got me teaching you strings and sequences, but we got our midterm coming up. So on Thursday, October 15th, there will be no lecture. And the idea here is that you can start practicing for the midterm. You can study, you can do our practice questions, come up with review questions. You know, if you have anything you want to ask about, bring it to our midterm exam review on Tuesday, October 20th. So it won't actually be me doing that. It'll be Marcus Darden. But you'll see me again after the midterm on Thursday. Meanwhile, your midterm is on Wednesday, October 21st. There is a midterm time sign-up form. So fill that out if you haven't already filled that out. It's on Piazza. All right, so with that, I think that's everything. Let's jump into the content. So yeah, this is EECS 281, lecture 13, strings and sequences. Now, a bunch of you have actually already seen some string stuff from project 1, but we're going to go a bit more in depth in this lecture. So just to start off, why should we study string algorithms? And well, what are strings? So strings are character sequences. So just an array of one letter after another. The thing you might not think about, though, is that it doesn't necessarily have to be characters from, say, the English alphabet. You could just as well have, one example would be where each character is a DNA base pair or something like that, or each character is an integer. So that is, when we're talking about a string, we're talking about a fairly general sequence of objects, where there's a relatively limited number of possibilities for each object. So it is still coming from some alphabet, even if it's not the English one. Now, why do we care about string algorithms? Basically, it comes down to applications. We're humans. We write a lot of text. We want to read text, search for text, manipulate text. And that's where string algorithms come in. So other things but it's not just text, right? So other things like, we might want to search for like license plate matches or something like that. And finally, a lot of string algorithms are also used in DNA analysis. So some things we're not necessarily that don't really fall into this category would be a sequence of like generic class objects or doubles. Okay, question in the chat. In principle, are strings really different from numbers? Characters are just numbers interpreted a bit differently, and strings are just vectors of characters. In principle, yes. They're not that different. Under the hood, everything is a binary number. But strings have an additional bit of structure to them that it's like a sequence of characters. So it's not a generic number. It has some structure to it. So what are all the different string algorithms that you might want? Some basic ones are comparing two strings. Are they equal or not equal? That's sort of what you did in project 1. Although I guess more in project 1 you did find where the strings differ. Another common string algorithm is ordering strings. Given 2 input strings, which one goes first in the dictionary? Another one is, what do strings have in common? Is one string a prefix of another? Can you find one string within another string? Another thing you might want to do is, if you have many strings, you might want to put them in lexicographic, there's a word for you, order. So that just means dictionary order. And the reason you might want to do that is it lets you look up words quickly. Obviously, when you open a dictionary, you don't have to just flip through every page in order to find the word you want. You can jump to it with just a couple of page turns and looking at a couple of words. Another super common thing to do with text is something that you all probably do when you're writing code, right? You hit Control F, or I think Command F if you're on a Mac, and you search for, say, a variable name. You want to find all the places in your file where a variable exists. And so that's the string search problem, where you have some short query string and some larger haystack that you're trying to find. So you're trying to find a needle in the haystack is the metaphor here. And there's some variants on this where, if you want, you can actually pre-process the haystack, pre-process your text in order to speed up the answering of a query. Does this shorter string exist in the text? And what do I mean by text here? I just mean a string, but it has some separator character which splits up the string into chunks that we will call words. And if we go up another level, we can talk about a text corpus, where now we have a collection of documents. So this is a situation where maybe you're in your IDE and you're searching for a variable across all the different files in your current project. Another example is web search, right? Every web page is just a document. And you want to search across many different web pages, billions of web pages, to find the web pages that match your search query. And so you might care about exact matches, but much more commonly, in web search, you want to do things like approximate matches. So if a word is misspelled, that might be one thing. In this example here, it says things to do in Ann Arbor. You might want to do some synonym replacement, where you replace things to do with the word, say, activities or events. And another thing that you also want to do once you get really advanced here is you want to figure out what the user meant when they wrote that query. So, for instance, in this example, it says, this weekend. The user is not looking for documents that contain the word this weekend. The user is probably looking for documents that are fresh, that are timely. So, obviously this is a huge industry of web search, Google and Bing and so on. Another text corpus problem is given, let's say project 1 submissions, can we find matches between the text submitted by one student and the text submitted by another student? And that's a tricky problem, because you don't want to just look for exact matches. You want to look for matches of chunks of each text, which are an approximate match. So even if, say, one variable has been renamed, you can still detect the similarity there. And so those are two examples of where we're comparing one text to another and determining their similarity. But for text compression, we're actually going to be comparing one text to itself, finding self-similarity. And what we're going to do is we're going to find basically repeated chunks of text, or repeated substrings of this string. And we're going to replace all instances of that substring with a short code. And if you do this enough, then you can really reduce the size of the file by taking out similar chunks of the file. Another example of string applications or string algorithms is a lot of stuff involving DNA. Because really, what is DNA? It's composed of these 4 base pairs: adenine, cytosine, thymine, and guanine, in a sequence. So it is a string. It's a fairly long string. It says, here I've got written 3 billion base pairs. And that sounds pretty long, and it is, but compared to, say, searching the whole web, it's a smaller problem, I think. And so things we might want to do with this DNA are, for instance, comparing 2 sets of DNA. Do they match? What are the differences? And you're going to use string algorithms to do that. So this might let you, for instance, in, say, medical research, compare, say, 2 patients' DNA to see if there's any genetic differences that can explain how they respond differently to some treatment. Another thing is when you are sequencing DNA, when you're reading in DNA, you get, I think, a bunch of short strands, short fragments of DNA, sequences, and you need to match those up. Basically, find some overlap in order to create longer DNA fragments and eventually have the whole DNA. So that's an overview of basically the types of algorithms that we care about here. And before we go into talking about the actual algorithms, let's get our minds thinking algorithmically. And let's answer this simple job interview question. So, you are shown one fruit at a time. And these fruits can be apples, bananas, oranges, or pears, but they can't be anything else. And you're given a string of n, of length n, where each item in the string is just one of these fruits. And the goal is to detect if there's a repeat in the string. And I'll pause for, say, 10 or 15 seconds to let you think about this total. All right, so maybe the first thing you think of is, what if I walk through the whole string and I count up how many apples, how many bananas, how many oranges, and how many pears there are in this string, right? And I think that's pretty similar to one of your labs. So if you take this approach, it's going to take O then time, because you have to walk through the whole string. But we can use the pigeonhole principle to actually answer this a little quicker. And the pigeonhole principle is basically a mathematical principle. Who knows where the name came from, but basically the idea is that you have, I guess, a pigeon coop, and there's different spots for each pigeon. And the idea is that if you have n spots, you can only fit n pigeons in before you have more than one pigeon in one of the pigeon holes. It could just as well be called the drawer principle. With putting objects in drawers rather than pigeons, but it adds a bit more color. And so the idea here is that since you only have 4 possibilities, right, apples, bananas, oranges, and pears, if you have a string that is longer than length 4, you will have repeats. So it's actually constant time, right? So you can check if the string is longer than 4, there are repeats. If the string is not longer than length 4, then you can go through and count. But count how many of each group there are. But since that for loop only iterates 4 times, that's constant time. So now let's talk about how you're actually going to use strings in your code. So C++ has my previous pen markings are showing up. C++ has 2 types of strings. One of which, the first of which, it inherited from C, which is this null terminated string. And this is perhaps the simplest string type. You basically just have an array, and each element in the array is 1 character. And at the end of the array, you put a 0. That's why we call it null terminated. And so, I mean, this has some trade-offs. The advantage is that it's very simple, doesn't take up really any extra memory. So basically, in addition to the length of the string, it takes 1 pointer to the start of the array, and you have to have that extra null character at the end of the array. But there are some downsides. If you want to compute the size of the string, you have to walk through the entire array counting up how many elements there are until you get to the null character. Also, it only supports ASCII characters, which is, fine, but it's not super modern, right? You can't put things like emojis in there easily. There's no Unicode support. So in the STL, and it's actually not part of base C++, but it was only added with the STL. We have our std string type. And so this essentially holds 2 pointers, the beginning and end pointer. There's some other stuff in the struct, but that's more implementation details. But what this lets you do is it lets you compute the size of your string in constant time. All you need to do is subtract these 2 pointers to get the length of your string. And so, we have plenty of different methods in our libraries that can work on both types of string, but definitely the type that you will use much more often in C++ is the STL string. One nice thing is that it supports iterator ranges. So this is kind of like a pretty common STL concept where a lot of STL functions you'll call by passing in a beginning iterator and an end iterator, rather than actually passing your object. And that's just to make things a little bit more flexible, and there's some fun tricks you can do with that we'll see in a couple slides. And yeah, finally, data structures for strings. So one of which is a dictionary. We'll talk about that more next lecture. It's not a string-specific data structure, but it is very useful for strings. So that lets you add, remove, check if a word is already in the dictionary, stuff like that. And another data structure that I don't believe we are going to get to in this class, but that is string-specific, is called a tree, T-R-I-E, not T-R-E-E. And this is essentially a prefix tree, where strings that share a prefix will be stored on similar branches of the tree. And so this lets you do stuff like a bunch of fast lookup stuff. So the first algorithm we're going to look at is equality of string. So we've got this STL function. You notice it takes in 2 iterators for the first sequence. So we've got our start iterator and our end iterator. And then for the second sequence, so it only takes in the begin iterator. So all that this function actually does is it compares the first first n characters, or the first last one minus first one characters of each string. In other words, it's checking not are these two strings totally equal, but is the first sequence the prefix of the second sequence. Obviously, if you want to check full equality, you can call this equals function, but also check are the strings the same way. So how might this function be implemented? Well, so the definition here is the same. We're taking in first one and last one, and first two, which is the second sequence. And we've got this for loop where we have this blank clause here. I'm not sure if you've seen this before, but basically it just means there's no initialization to be done for this for loop. Then our loop condition that we're going to be checking is that first one is not equal to last one. In other words, we have not reached the end of our sequence. And then when we increment, we're going to increment the first sequence and the second sequence. And this is because we want to check, that corresponding characters match for both sequences. So then inside the loop, all we do is check exactly that. Yeah. If the two characters don't match, we can exit early, return false. On the other hand, if we make it all the way through the for loop, then the strings match, or at least all of string 1 matches the beginning of string 2. String 2 could be longer. And so here's a fun example of using sequence equality. Here, what we're trying to do is we're trying to detect palindromes. A palindrome is a word that you can reverse, and it will still be the same word. So we're going to use this equal function we just defined, and we're going to call it in an interesting way. So for the first sequence, we're going to give the begin pointer as s.begin. But then instead of giving s.end here, we're going to do s.begin plus s.size over 2. In other words, this first sequence we're giving equals is just the first half of the word. Then the final argument is s.rbegin. Now, I don't know if you've seen this before. Some of you may have. But this is a STL concept. It's a reverse iterator. So this iterator actually starts at the end of the word and works its way backwards as you increment it. So you increment it to go backwards. So what this call to equals is doing is we're checking if the first half of the word equals the word reversed, or equals in the sense of x2 equals, where it only checks the first part of the word. So this will print out for radar. It'll print out radar is a palindrome. For hello, it'll print out this is not a palindrome. So that's equals. Next, we're going to talk about the less than operator for string. And this is defined differently than, say, comparing numbers. But it's something that you're very familiar with because this is just dictionary order. So if you have two strings, say A and AB, A comes first because it's shorter. But if you have a string AB and a string B, B comes after AB because the first character is greater. Sorry, that might have been a confusing way to say it, but it's a concept that I think you're all familiar with. So why do we care about just equals and less than? Is that you only actually need these two operators. All of the other operators that you care about, such as not equals, greater than, less than or equal to, greater than or equal to, can be implemented just using equals, less than, and negations. And one important thing to note here is that each of these new comparisons only requires us to call either equals or less than. We never call both operators. So we're never taking that extra cost of calling a second operator, because since these operators are on strings, their runtime is proportional to the length of the string. So actually, under the hood, we might implement both equals and less than as the same function, called, or commonly called, something like compare helper, where you take in, and this isn't just for strings, this is for any types that you might want to define equality or less than for. You might define compare helper, where you take in, two objects of type t, and you're going to return an int that will be 0 if they are equal, -1 if x is less than y, and 1 if x is greater than y. So let's say you're writing this for integers. All compare helper has to do is it can return x minus y, right? Because if the two integers are equal, that'll be 0. If x is less than y, that'll be negative, and so on and so forth. Right. Oh, yes. I didn't mention that. It doesn't necessarily have to be -1 for x less than y. It just has to be some negative number. Yeah. Question in the chat. Essentially, this is essentially what we did in project 2 for our comparator, right? Yeah. This is very similar. Yeah. So typically, once you have this compare helper function, you would then call it in your implementation of the equals operator or the less than operator. And just a couple notes on, I guess, optimization. Well, this first note here isn't really something that you have to think about, but you should know that it's happening behind the scenes, which is that STL strings don't actually use dynamic memory if the string is short enough. And that just lets us keep everything, all of our memory accesses nice and local. Another thing is that, well, yeah, optimization note 2, for C-style strings, because we have that null character at the end, when we're walking through, say, ABC and ABCD, we'll automatically get, we don't necessarily have to directly check for the end of the string. We can compare that 0 character to D. 0 is obviously less than D, and so ABC will be less than ABCD. Another optimization tip that you probably already use in Letterman is that strings of different size are not equals. And finally, this is not something we'll go over in this class, but if you really care about speeding up these sorts of comparisons, there are special instructions that are used for string comparisons. Vectorization is a technique. I mean, basically all it means is you're calling special CPU instructions that operate on multiple pieces of data at once. They're also called single instruction multiple data commands, or SIMD, which is, if you want that last bit of performance in a busy loop, that's where you look for it. So let's see an implementation of this compare helper function. We're going to take in two strings, S0 and S1, and we're going to have this for loop that runs for the minimum of each of their lengths. And what it does is every single character, it'll check basically if the character for string 0 is less than the character for string 1, return -1. If it's greater, again, do an early return. And otherwise, you're just going to keep looping. And so you'll get to the end of one of the strings. So then the last thing you have to compare is which string is longer in order to determine which string comes first in the dictionary. So what is the runtime performance of this function? So you'll notice we have this one loop here, which runs for the minimum of the two string lengths. So this is O of the minimum of the length of the two strings, or really O of n. But this is the worst case, right? Where you have to compare all of the characters in the string and you can't return early. So it's interesting to think about for random strings, the average case complexity is actually O of 1 because most of the time you're only going to need to look at the first few characters of the string in order to determine that the two strings are not equal. And you can actually calculate what the probability of the strings matching at each character is and use that in improving this statement. However, in the real world, strings are usually not random. So you might have file names, which unfortunately are kind of the worst case, where you have this really long shared prefix before having a final character that differs, or something like that. On the other hand, you might get lucky other times in the real world. For a lot of words, you're going to have maybe the best case coming up where the prefixes differ. Something to think about is, what if we compare nearby words in a dictionary? Is that going to be closer to O of n, like worst case, or closer to O of 1, best case? And I'll pause for a second to think about that. Okay, so there's a question in the chat about how would you prove that generally? What is a random string, and can't the alphabet depend? Right. So by a random string, I mean something where each item in the sequence is drawn at random from some collection of items, which we're going to call the alphabet. So in the case of English, this collection of items is just letters A through Z. And you're right that it does depend on the size of the alphabet. The probability of two random strings matching does depend on the size of the alphabet. So if you have a larger alphabet, obviously the strings are going to be less likely to randomly match in the first character, or in any character. So for the dictionary question, let's say you compare the word starting at the beginning, that's going to be close to O of n time, because the words are going to share almost all of their characters starting from the beginning, right? Usually they're going to have the same prefix, like stop and stop sign are probably next to each other in the dictionary. There's a question in the chat, closer to O of 1, I think. Assuming you look at the end of the strings first, since the start of the strings are almost certain to be the same. Right. So definitely there's tricks you can do. Right. So in the STL, we have this sort of lexicographical comparison that is doing this dictionary ordering that we talked about. But you notice it's not saying string first one, string last one. It lets you do whatever sort of sequence you want, as long as you can pass this iterator range where you have the beginning iterator and the end iterator. And you'll also notice that unlike the STL equals function, here we do have to pass in the end iterator for the second sequence, because we do need to know the length of the strings to determine their dictionary ordering. And there's some stuff here about execution policy, but let's not worry about that. Let's we'll look at an implementation that doesn't look at that. So the rules of Lex Compare are essentially what we just laid out for dictionary comparisons, which is that we're going to compare element by element, and the first mismatching element lets us say which range comes before the other. And then, of course, we've got these edge cases about empty ranges. But let's look at the implementation. So this is how it might be implemented. we've got our inputs of the first begin and end iterators for both strings. And then we've got our for loop. Again, no initialization clause in the for loop. This time we're going to check that we haven't reached the end of either range. And then obviously we're going to increment both begin iterators. Again, we'll return early when we find a mismatching character. And then finally, we've got this one-liner here that checks the lengths. So if first one equals last one, that means we've reached the end of string 1. So the only thing we need to check then is have we reached the end of string 2 or not? So if we have not reached the end of string 2, then we will return true because the first string is shorter. And they share the same prefix. So the first string should come first in the dictionary. Otherwise, if they're equals, we'll return false because string 1 is not strictly less than string 2. So here's kind of a fun example using Lex Compare. We have two vectors of chars. So not quite the same thing as the string type, but very close. Okay, there's a question in chat. Let me go back. Shouldn't the for loop dereference the iterators when comparing? And I believe it is. So we have star first one and star first two. Oh, you mean the last compare actually, right? So here we're checking not if the character at first one equals the character at last one. We're checking essentially the pointer addresses. So is the first one pointer pointing to the same spot as the last one pointer? In other words, is the first one pointer pointing to the end of the string? So have we reached the end of the string? Okay, gotcha. Right, so we've got this example using Lex Compare, where we have two char vectors. So essentially two strings, but we're representing them a little bit differently here. And this line looks a little funky. What we're doing here is we're just creating a random number generator. And what we're going to do is while not std lexicographical compare of these two ranges, we're going to loop. So in other words, while the first range doesn't come before the second range, we're going to loop. And what we're going to do inside is we're just going to print out each of the ranges, and then we're going to shuffle each of the ranges. So basically just randomly rearrange each of the ranges. And so this process is going to loop until we get some ordering of the characters that makes range V1 lexicographically less than range V2. And then we'll just print it out and exit. Oh, I accidentally went back there, but I meant to just put the laser pointer here to show where it's printed out. So when might you use Lex Compare? Well, there's many uses, but one application is for removing duplicates. So if you have a vector of strings, what you can do in order to remove duplicate strings in that vector is you can sort the vector using a lexicographical ordering, and then in a single pass through, you can check if neighboring elements of that vector, if neighboring strings are equal to each other. And if you copy only the first of these duplicate strings, you're only going to get the unique strings from that original collection containing duplicates. Next lecture, we'll probably also talk about a different way to remove duplicates from a set of strings, but using dictionaries and hashing. So now let's talk about text search. This image is pretty fitting. You often want to find something small, a needle, in something large, a haystack. So there is an STL function that does this called find. And what this does is it searches for the first occurrence of some string within another string. And so this is a member function of string. So that's why there's only one string argument, which is essentially the query string. So how does string searching work? So perhaps the simplest way is to do brute force, where you have two nested loops. And essentially what you're going to do is you're going to be checking a nested window where, let's say this is your query string, ABCA, and this is your target string, some longer string. What you're going to do is you're going to check, basically your outer loop is going to define the start of the window. So you're going to start off with your window going from A to D. On the second iteration, it's going to go from B to base, and so on and so forth. And your inner loop, what it's going to do is it's going to check, does A match A? Yes. Does B match B? Yes. Does C match C? Yes. Does D match A? No. Unfortunately, this is not your match. So you go back and you shift. So now we're comparing A against B. And that's what we mean by sliding window. Obviously, in this case, A doesn't match B, so we can break early. We're going to shift this whole thing down one more character, compare A against C, compare A against D, and eventually we'll get to comparing A against A. And actually, that won't even end up being a match. But eventually, when we have our window all the way down here, we'll have found the match. So the way this is implemented, in the worst case, we do have these two loops nested inside of each other, one of which iterates len haystack times, and the other of which iterates len needle times. So our big O performance will be on the order of len needle times len haystack. And you can see the worst case pretty clearly in a case where we have, A, B, right? So, and we're checking it against this string. Every window, we're going to have to go basically to the end of the query string before we can say that the query doesn't match this location in the target string. However, for, again, random strings, this is much, this is not quite so bad. It's just order of length of haystack, because the inner loop is only going to take one time, because most of the time the strings are going to have some difference, or rather the query is going to have some difference when compared to the window in the first few characters. So this is a pretty good string search algorithm. It does have that potential worst case downside. There is another algorithm, this Morse-Pratt algorithm, that uses a little bit of additional memory in order to reduce the run time to on the order of length of needle plus length of haystack. And essentially what that does is it essentially figures out subsequences in the query string ahead of time so that it knows basically how much it needs to backtrack when it doesn't have a match, or how much it can skip ahead, when it doesn't have a match from a partial match. But we're not going to go into that in this class. Instead, we're going to look at a different idea, which is to try to just speed up the best case, or for some of the known worst cases as well. to put it another way, we're going to try to make the best case happen more often. So we're going to try to perform most equality comparisons for the strings in O of 1 time. So how do we speed up this equality comparison of strings? Well, there's kind of a big idea here that should be a takeaway, and that will also come up next lecture, which is we're going to compute a string fingerprint. So for each string, that's a very wobbly line. For each string, we're going to compute a number, an integer, that we call the fingerprint. And so the idea here is that if the fingerprints, we're going to compute the fingerprints in such a way that if the fingerprints are different, the strings must be different. They are guaranteed to be different. But when the fingerprints match, there's some chance that the strings could be the same. Or sorry, when the fingerprints match, the strings will most likely be the same, but there's still some chance they could be different, and we will, in that case, have to check character by character whether they are actually equal or not. And so typically this fingerprint number doesn't actually really mean anything. It's just a number we compute purely for the purpose of speeding up comparison. So there's many different ways to do the fingerprint function, and that's honestly a huge topic that you can look into more if you want. But one example of maybe the simplest possible fingerprint function is to take each character in your string, get its ASCII code, and just add them up. And so this will work, right, to a certain extent. One thing that it doesn't take into account is the position of your characters in the string. So Tom Marvolo Riddle has the same fingerprint as I am Lord Voldemort because it consists of just exactly the same letters in a different order. You'll notice that unlike in the Harry Potter books, we have added a space here because the ASCII value of a space character is non-zero, so it does matter for this fingerprint function. So we'll see a better fingerprint function in a sec, but first, well, I kind of already mentioned this, but basically, if we, what can we use these fingerprints for? So if we had a pretty good fingerprint that has few collisions, which is going to happen most of the time for the fingerprint functions that people commonly use, then you can solve the problem of finding duplicates in strings. So for each string, you can compute its fingerprint, and then we can do that same sorting thing, except now we're going to sort the fingerprints instead of the strings themselves. Then what we can do is we can walk through the fingerprints, and now we only need to check full string equality when the fingerprints match instead of every time. All right, we have a question in the chat. Suppose you decided to interpret a string as a base 127 number with each character as a digit, converting each string to a number. Assuming space wasn't a concern, would that be a better fingerprint? Well, that's essentially what we have on the next slide, actually. So the idea is exactly this. We're going to view strings as decimal numbers, right? So, basically, quick refresher on decimal numbers, right? You have, say, some number, 123, right? But we just write that 1, 2, 3. But we know that what this means is really 1 times 10 squared plus 2 times 10 plus so on plus 3 times 10 to 0. And so we're going to apply the same idea to string, where we're going to take each character and eventually multiply it by 10. So if we want the fingerprint just of the first character, that's still going to be just ASCII code 84. If we want the fingerprint of the first two characters, that's going to be 10 times 84, which is the character code of T, plus 79, which is the character code of O. And then obviously, if we want to do the fingerprint for T, O, M, it's there, and then, et cetera, et cetera. So the nice thing about this is that if you reorder the characters in the string, your fingerprint will usually change. So this is a much more precise fingerprint function than the previous one. Typically, you'll use some larger number than 10, which will also improve the quality of the fingerprint function. And I see a question in chat about int is only 32 bits. Would this limit the string's length? And the answer is yes, it would, but we have another trick that we'll get to in 3 slides for handling that, the overflow problem. So one other nice thing about this way of fingerprinting is that adding a new character only takes O of one time because we can reuse the work we already did. Right, so if we've already calculated the fingerprint for T, which was simple, that's just the number 84. We can now take our previous fingerprint value, multiply it by 10, and add the ASCII code of O. And we can repeat this process to get the fingerprint of the whole string in O of n time, because adding each character only takes O of one time. The part that may not be so obvious is that removing a character on the left also takes only O of one time. So let's say we have, okay, so here, for example, we have our fingerprint of T, O, M. In order to remove T, we simply need to subtract T times 10 times 10. And so if we pre-compute this value of 10 to the m minus 1, where m is the length of the original length of the fingerprint, then removing a character is just one subtraction, so this is constant time. And so this leads us into a faster way to string search, to find some query string in a larger string. So here's a high-level overview. We'll see the code in a second. Step 1, we're going to compute the fingerprint of the needle. Step 2, we're going to take a window of the haystack, and we're going to compute its fingerprint. And then all we need to do is we check if the fingerprints are equal. If they're not, we'll loop and we'll slide our window along. However, there is still this case where sometimes the fingerprint of the window will equal the needle, and then we actually do need to check full string equality between the window and the needle. But most of the time, we're just going to be doing this very fast check of, is the fingerprint of our window equal to the fingerprint of the needle? And the other part of this algorithm, of course, is efficiently computing the fingerprint of the window as we slide it along. So because we can remove one character on the left and add one character on the right in O of one time, this is very efficient. Now, to get to the question from the chat about overflow and the length of the string, right, if we keep on adding and multiplying numbers, eventually we're going to overflow. So what we're going to do is we're going to replace conventional arithmetic with modular arithmetic, which I assume most of you have already seen from, I think, 203, but I'm not totally sure. But this is essentially clock arithmetic, where 11 o'clock plus 4 o'clock equals 3 o'clock, not 15 o'clock. So rather than using x times y in the algorithm for updating the Rabin fingerprint, we're going to do x times y modulo some large prime number. Now, obviously, when we do modulo some prime number, we're reducing the number of possible values that our fingerprint can take on. So, for instance, you wouldn't want to choose, say, number 2 as your prime, because then you'd only have 2 possible fingerprint values. So you want some largest prime. This will give us more equal fingerprints. So is there an optimal size for the prime? Honestly, as long as your prime number fits in your 32-bit integer, I think the bigger the better. So here's an example of what this Rabin cart string search looks like in code. So we're going to take in a needle, a string needle, and a string haystack, as well as some prime number that we're going to use for our modular arithmetic. And here we're going to use base 128 instead of base 10 like in the previous slides, because 10 is really just too small to use here. So we've got some initialization of variables here. We're going to pre-compute the value of our base, 128, to the length of the needle minus 1. Right? We're going to use that, remember, for removing values from the fingerprint on the left. Then we've got this for loop. And what this does here is it computes the fingerprint of the needle, and it computes the fingerprint of the haystack by going character by character and adding each new character into the fingerprint. So then we've got really the body of the search, where we're going to loop over the haystack, moving our window along each time. So every time through, if our fingerprints are equal, we need to do this for loop, which is length of needle, in order to check if the fingerprints are equal, the needle could potentially be a match here. So we need to check that. So we need to check every character. And if the match is a real match, if it's not a false positive, we will return early. I'll get to the questions in the chat after finishing going through this algorithm. So on the other hand, in this for loop, if the fingerprints didn't match, or if when we did our actual full check here, that didn't match, then we're going to step our window along, and we're going to we're going to update our fingerprint in constant time with this little one-liner here. And I'll go through that step by step. So the first thing here is we're going to remove the character on the left. So we're going to do our fingerprint minus the character on the left times our pre-computed value of the base to n minus 1. And then we're going to do modulo our prime number. Now that we have our reduced fingerprint, we're going to multiply it by the base, and we're going to add this new character into our fingerprint. And again, we're going to take everything modulo prime. The last thing we need to check here is potentially if h has become negative. We just are going to fix that by adding prime to it. So this ensures that at the end of computing our fingerprint, we're going to have a value for h, which is somewhere between 0 and the value of prime. And that's basically it for a faster string search. And remember, this is faster in the best case. If your fingerprint function is bad, this could still be the worst case of checking of having the whole algorithm take on the order of length of needle times length of haystack. So let me address the question in the chat there about prime number. Let's see. So we have a question, why should we use a prime? Why not a composite integer? How does using a prime number eliminate an overflow? Wouldn't the number just naturally wrap around to 0 when it reaches the upper limit? Why does using a prime number work better? So I think it's really just the question here, why use a prime, right? Because yes, the number would naturally wrap around to 0 if we just let it overflow. If it is an unsigned integer type, that works fine. But then effectively what we're doing is we're taking a modulo with respect to a non-prime number. So the question really comes down to why do we care to use a prime number here? Yeah. And the answer to that is that we want to essentially for long fingerprints, where you are wrapping up for a bunch, we want to prevent pattern in the fingerprint. So let's say you're fingerprinting a string that you expected to be a normal English language string, using all the letters and everything. But you're some user of your system has decided to be funny, and they've given you a string that's just A, B, A, B, A, B, A, B, A, B, A, B. In other words, it has this pattern. The problem with using, or even if it's just all A's, the problem with using a non-prime number is if your number that you have chosen is a multiple of the ASCII value of the letter A, when you take that modulus, when your arithmetic wraps around, you'll end up back where you started, right? So let's say the value of A is 50, and instead of using a prime number here, we've gone with the number 100. As you fingerprint this string, character by character, it's going to go 50, back to 0, 50, back to 0, 50, back to 0, if you're just adding the numbers together. So your string is actually not going to take on all the different possible fingerprint values that it could take on. It's not going to take on all the values between 0 and 100. So on the other hand, if you used prime number there, this won't happen. Because when you wrap around, since there's no common factors shared, you're not going to wrap around to the same spot that you were at previously if you just keep adding the same character in this way. So I mean, it's kind of a detail, right? Like, this situation won't necessarily come up that often. But, why not use a prime? Especially because, sometimes you need to make sure that your fingerprints are equally good for a broad range of different strings that users might put in, right? Like, let's say you're Google and you're checking if strings are equal at web scale, and somebody gives you the search query that's just A, or something like that. And then because your fingerprint function breaks down, now you have to do a full string comparison at every spot in, or every time through the outer loop. You have to do this full string comparison, and now, your servers are on fire because you didn't have a good fingerprint function. And we'll talk more about hash functions and fingerprint functions next time. But that's the rough idea. So this is actually the last slide for the day. I guess we're ending a little bit early, which is just the complexity of reading carve. And we kind of already talked about this a little bit, but basically, if your fingerprint function is perfect, in other words, if you never have false positive matches between your fingerprints, this will be on the order of length of haystack. But every time you have a collision, that's going to cost you on the order of the length of needle. In practice, you can make collisions pretty rare, And so this is quite a good string search method. So that's the end of strings and sequences, lecture 13. So just as a reminder again, maybe for the people who came in late, there's not going to be any lecture on Thursday because we expect you to start studying for the midterm exam and to go over the practice questions and come up with questions to bring to the midterm exam review with Marcus Darden on Tuesday, October 20th, for your midterm on Wednesday, October 21st. Also, don't forget to sign up for a time for the midterm in the form on Piazza. And that's it. Have a good day, everyone.